Hey guys, welcome back. This is going to be part 3 of those drag notes. Again, I'm going to take this and put it down so it's out of the glare. All right, so if the block again is released from rest at the top of the incline when it reaches a horizontal surface, is moving with the speed of v naught. Now suppose the block experiences a resistive force as it slides on the horizontal surface. The magnitude resistive force is F equals beta v squared, where beta is a positive constant with units of kilograms per meter. Right, but do not solve a differential equation for the speed of the blocks on the horizontal surface. So, on this horizontal surface, we have beta v squared. So I'm going to do that F net is equal to MA. And I'm going to do that negative beta v squared is equal to MA. I'm going to rewrite A as dV dt. And I'm going to get dt and m over to this side with beta. And I have dV over v squared. So that's part B, or the first part of it. Using the differential equation from part D, show that the speed of the block vt as a function of time can be written in the form of 1 over vt equals 1 over v naught plus beta t over m. Okay, so I should put my integral signs in here, right? And this one's going to go from v naught to v. This one's going to go from 0 to t. All right, so on the one side, we're just going to have negative beta over m times t from 0 to t. So that's just going to give me negative beta over mt. On the other side, I'm going to have, when I do this, this is really v to the negative second, right? So I need to add a power. So it's going to be v to the negative first. When I take the derivative of that, I'm going to get a negative 1 in front, so I need to cancel that out. So I'm going to have negative 1 over v from v naught to v. And this is going to be negative 1 over v naught minus negative 1 over v naught. So I have that negative beta over mt is equal to and I'm going to multiply everything by negative 1 to make it a little bit easier because I'm trying to get somewhere. I want to be there. So when I multiply both sides by negative 1, I'm going to add that to the other side. So I'm going to have 1 over v naught plus and I'm allowed to put this t in there, right, because it's a function of t. I would always encourage to write the free body diagram out because you want to make sure, like when I put this in my F net equals MA, that this is a negative force. So I want to make sure that I'm recognizing that because otherwise we wouldn't get to the end spot. All right, sketch the graph's position of x as a function of time, velocity v as a function of time, and acceleration a as a function of time for t as the block is moving on a horizontal surface before it reaches the spring. All right, so the acceleration is going to start at a maximum because that's the fastest I'm going to be going, and then it's going to decrease because I'm going to start slowing. So as the velocity decreases, it's going to give us less acceleration. My velocity is going to start at a maximum. It's also going to decrease, right, because the air resistance, the drag force is decreasing it. The distance, we can start as 0, and it is going to be getting further away from the edge of the ramp. Now, for the distance, since the velocity is decreasing, that means that I need to have a curve that represents that my slopes are getting smaller. Now my velocity is decreasing, but so is my acceleration. So I need to have a curve for velocity that's getting smaller, and it has to have decreasing slopes. And then my acceleration is getting smaller because it's related to velocity. A box of mass m initially at rest is acted upon by a constant applied force of magnitude F of A as shown in the figure above. The friction between the box and the horizontal surface can be assumed to be negligible, but the box is subject to a drag force of magnitude kV, where V is the speed of the box and K is a positive constant. Express all your answers in terms of given quantities and fundamental constants as appropriate. The dot below represents the box. Draw and label the forces, not components that act on the box. So I have F of A, and I have, sorry, not KX. Get in the, I have KV going back in. Write but do not solve a differential equation. And are you seeing a trend here of what they're asking you to do? A differential equation that could be used to determine the speed v of the box as a function of time t. If you need to draw anything other than what you have shown in part A to assist in your solution, use the space below. Do not add anything to the figure in part A. What does that mean? That means if something's at an angle, don't break it into components on the free body diagram, because it ceases to be a free body diagram. So even though there's an angle, they include that with every time they have free body diagrams. All right, so F net equals MA. FA minus KV equals MA. FA minus KV equals M dV dt. So again, we're substituting in for acceleration our change in velocity with respect to time. Now I want to get this over here and dt and m to the other side. So I'm going to have dv over f of a minus kv by one integral. On the other side, I'm going to have dt over m, or 1 over m integral of dt. Do they ask us to integrate? I don't know. I'm going to go forward. Determine the magnitude of terminal velocity of the box. Okay, so terminal velocity of the box is going to be when the acceleration is 0. So F net equals 0. FA minus KV equals 0. FA equals KV. V equals FA over K. And I can give it a little nice subscript for terminal. Assume the differential equation from part B to derive an equation for speed of V as a function of time. Assume V equals 0 at time t equals 0. All right, so I'm going to integrate this. From 0 to t. And from 0 to v. All right, so again, I'm going to do a U du substitution for this, and I'm going to let U be equal to FA minus KB. And that means that du is going to be equal to negative K dV. So that means that dV would be du over negative K. So when I substitute this back in, I'm going to get the integral of du. I can take the K, negative K out front, and I have du over u from 0 to v. All right, so on this side, I'm going to have just t over m. So I put in a 0, that's going to cancel out. On this side, I'm going to have negative 1 over k from 0 to v of the natural log of u. I think that I didn't want to make it a definitive integral. I think that I just want it to just be thinking about this, because they're telling us that the velocity is 0 when u 0. So we'll take that out. So that's going to give us the natural log of u plus c. So that's going to be the natural log of FA minus KB plus C. And they're telling us that when t equals 0, b equals 0. Which I misread as they wanted us to go from 0 to whatever. So if I put in a 0 over here, this is going to be 0. So C is going to be 1 over K, the natural log of FA. So I can rewrite this as T over M, negative 1 over K, natural log of FA minus KB plus 1 over K, natural log of FA. So if I were to, I can get the K to the other side. And then if I remember my natural log rules, subtracting is like dividing. And then I want to take e to either side to undo the natural log. And I'm going to get e to the minus kt over m. It's going to be equal to FA minus KB over FA. And then I'm going to multiply both sides by FA. So I'm going to switch this term and that term, which is going to give me KB is equal to FA minus FA e to minus KT over M. And so V of T would be equal to FA 1 minus e to negative kt over L over k. Sorry about that definite mix up in the beginning of that. But that's our answer. All right, on the axis below, sketch a graph of the speed v as a box of function of time, explicitly label any intercepts, asymptotes, maximum, minimum with numerical values or algebraic expressions as appropriate. So we're starting with a speed and our acceleration should be decreasing because as it speeds up, the drag force is going to get bigger. And so I should be having a less steep line, and it should be a horizontal line at VT, which would be our terminal velocity. An amusement park ride features a passenger compartment of mass M that is released from rest at point A, shown in the figure above. It moves along a track to point E. The compartment is in free fall between A and B. And B are distance 3r over 4 apart, then moves along a circular arc of radius r between points B and D. Assume the track is frictionless from A to D. The dimensions of the passenger compartment are negligible compared to R. On the dot below that represents the passenger compartment, draw and label the forces, not components, that act on the passenger compartment when it's at point C. Point C should have a normal, and it should have and this should act perpendicular, right? That's what normal means. In terms of theta and the magnitude of forces drawn in part A, determine an expression for the magnitude of the centripetal force acting on the compartment in point C. If you need to draw anything besides what you have shown in part A to assist in your solution, use the spaces below. Do not add anything to figure part A. So I'm going to do it back here so I can look at what I have. All right, so the center of my circle's here, so n's in that direction. I'd like to find the component of weight that is in the opposite direction. So I know that, let me draw this over here so I don't touch my free body diagram. There's two components of weight. There's one that is opposite the normal, and there's one that is directed tangentially in that direction. Those two together would make up the total weight. And I know that this angle is theta. I know that this is a right angle. So I know this angle is theta. So I know that this angle is theta. So I know that this is 90 minus theta, the one inside of here. So this one down here is theta. So that side is the opposite side of theta. So I'm going to have F net equals mv squared over r. I'm going to take the forces in minus out. In is n, out is going to be mg sine of theta. Derive an expression for the speed VD of the passenger compartment as it reaches point D in terms of MR and fundamental constants. So D is down here. So I would say that energy is conserved. At the top, I would have potential. At the bottom, I would have kinetic. And we're saying that the total height is R plus 3R over 4. So that's going to be 7R over 4. So I have mg 7 over 4R equals 1/2 mdv squared. So I'm going to cancel that away. I'm going to multiply both sides by 2. So now I'm going to have 7/2 GR square rooted would be VD. A force acts on the compartment between D and E and brings it to rest at point E. If the compartment is brought to rest by friction, calculate the numerical value of the coefficient of friction between the compartment and the track. So it's going to go 3R. So work is going to be equal to the change in kinetic energy at fric times 3R is going to be equal to negative 1/2 mdv squared. We said that this was the square root of 7/2 GR. I'm going to go back and make sure that's what it is. I think it's 7/2 GR. Yep. So this is going to be negative 1/2, 7/2 GR is equal to F fric times 3R. So F fric is going to be equal to negative, I have 7/4 divided by 3 is going to be 7/12 mgr. This is also equal to mu n. And n is mg in this case. Now it's nasty negative because this should have been negative too because it's a resistor force, right? Our mu is not going to be, it's unitless and it can't be negative. So I have 2 mg's and the negatives can go away. And so mu is equal to 7/12 R. Now consider the case in which there is no friction between the compartment and the track, but instead the compartment is brought to rest by a braking force negative kV, where k is a constant and v is the velocity of the compartment. Express all algebraic answers in terms of m, r, k, and vd and fundamental constants appropriate. Write but do not solve the differential equation vt. I'm going to stop again because this period's almost over. So I'll pick up at this point. I apologize, but we're about 25 minutes through